Based on my ergonomic keyboard endgame video, I'm now going to do a bit more of a deep dive into the process of actually designing the PCB using Ergogen and KiCad. So I did a little bit of a walkthrough in that video on this process, but in this video I'm going to really focus in and look in detail at all of the things you need to get your head around when you're going to be designing a PCB here. This video is really kindly sponsored by PCBWay, who manufacture PCB boards, so we're going to be using them as the example through this video as to how we're actually going to set things up when we place the order for the PCB. So the idea is PCBWay will accept a Gerber file and you upload this file, and that's everything they need to manufacture a real life PCB that they send to you in the post. I'm very happy to recommend PCBWay. I actually used them for the Ferris sweep keyboard video that I did. They're super friendly to work with and really efficient and very fast to build these things and get them posted to you as well. They do not only PCBs but also 3D printing and CNC and a whole range of other stuff in terms of fabrication and building these things. So very cool company to work with. Very happy to recommend them. So you can make one of these Gerber files in KiCad, which is a free piece of software that builds PCBs, and you can actually work entirely in KiCad to do this. But that's pretty complicated. So we're going to use alongside that this program called Ergogen, which is this amazing little tool that takes you most of the way there and gives you a project that you can open in KiCad and finish off. So I've developed a little framework that I'm building these custom keyboards within, and that is that they've all got under 36 keys across both halves. They are split, fully wireless, of course, using the nice nano controllers. And the switches are hot swappable, so we've got the hot swap sockets on the back there. And then they've got the slider switch for power, a little reset button to make it easy to reset the controllers when you put new firmware on, and a battery connector so you can quickly take the battery off. So the idea with all of that is that you can actually take it all off, take the keys, the battery, and the controllers off those boards and move them very easily onto another board that you might design in the future. So we're going to jump right in and take a look at this Ergogen front end here. So this is ergogen.cache.works. And you can see on the left here we've got some sample code, and we're just going to get rid of all of that so that we can build it back bit by bit and really understand what we're looking at here. So this is this YAML file, which is the indentation is obviously really important here. And we've got points, and then within points we're going to have zones, and we've created a zone called main. Now that's just our own name for it. You could call it whatever you want. Essentially it's to represent a collection of keys. So this is going to be the main grid of keys. So then you define rows and columns, and within the rows and columns you're just simply creating new names to represent those rows and columns. So under rows we've added bottom, home and top, and under columns we're now just going to add a name for each of the columns we want. So we're going to go ahead and add 5 columns here, but if you wanted more you would just simply carry on going and add another name for your additional column. So you can see that grid has been created there by the 3x5 naming of those rows and columns. So inside the pinky column here, we're now going to use this row overrides item. So we pop that in, and that just basically means that column is then going to ignore the rows definitions and it will work with its own. So if we just add the one item there, bottom, you can see that that is only adding the single key in that column now. Now if we just look at the middle column here, we're seeing what we're using now is we're actually putting the rows property underneath that middle column, and that means we can target individual keys inside that column. So if we add a rotate property here to the bottom key, we can see we've targeted just that key, and we're now just adding the rotation to that single key. So we can see this is now basically this little block for the zone that we've created. Now, if we go right back up to the top level, we can actually add a new area here called key. So because it's directly underneath the points area, it's going to apply to every key. So this padding value, CY, is the default for a chock switch, which is the vertical padding between the keys. So you can see the preview actually looks like it's overlapping those a little bit now. And that's just because the default is a MX style keycap. So they now look like they're overlapping because we're using the chock spacing. So what we're doing now is adding the spread value to each of the columns, and that's actually doing the same thing for the horizontal. So we're bringing them all in horizontally. Now in this case it's actually just making the key outlines look like they're just touching, but in reality again there's going to be a tiny gap because we're just using chock spacing, but the preview is using an MX size. So let's go ahead and add this thumb zone. So the zone here is going to be just for the thumb cluster. So we're now defining a new grid essentially of rows and columns, and we're calling it thumb. So we're going to go ahead and add this anchor property, which is how we know where it's going to be positioned. So in Ergogen, everything is kind of relating to something else. So we're going to position the thumb cluster zone based on the main zone position. And you can see the ref value here is based on the name of a zone, the name of a column, and the name of a row, so with underscores between them. So we've got main far bottom, and that means the reference point for this anchor is that bottom right key of the main zone. And then we can add this shift property, which is an array of two values here, X and Y position. You can see we then move it based on the distance from that reference key. So we've targeted the bottom right key, set the shift up to move it down and right from that key. Then we can rotate this whole zone just by adding the rotate property there. And we can rotate individual columns by putting the rotate property under the columns here. Now you can see because we've rotated that key, it's sort of bumped into it. So we want to add a bit more spacing. So we're just going to use the spread property here. And we can use the CX as a starting point and then modify it by adding the 1.5 to it. And you can see that's nudged it over a little bit. And we can use this stagger property here to shift the sort of vertical alignment between the columns. And we can do this in any of the zones, basically. This is a nice way of just adjusting that vertical offset from one column to the next. So essentially, whichever column you add that stagger value to, it will move it based on its column to its left. The other way of looking at it is to use the shift item, which has that XY value in the array there. So we're just going to leave that one as stagger for now. And we're going to go ahead and add the stagger to the columns in the main zone. So because it works from left to right, the leftmost column here doesn't actually need anything defined in it. We're just going to go straight into the ring column for the ring finger, enter the stagger value here. And you can see it actually appears to be moving the pinky column, but if in effect what it's doing is moving the ring finger column and then everything else follows on from there. So once you get your head around how that sort of works, you can see, so we're now adjusting the middle column, but it looks like, again, it's actually just adjusted the ring column. But if you think about it, all it's doing is just moving that column, and then everything else to its right will follow its position. So there's no difference to its right, it only appears to move to its left. So if you add the rotate property to an individual column, the same thing happens. It rotates it, compared to the column to its left. And you can actually add the rotate property to a whole zone, and that will just change the whole thing here. And because the thumb cluster is attached to a point within the main zone, changing the rotate property inside the main zone here will affect the thumb cluster as well. So essentially, when you're building your keyboard layout here, you're working with the stagger value and the rotate value for your columns. And that's how you can kind of set up this, really ergonomic, super ergonomic keyboard layout that matches your hand. And obviously, you kind of come up with how much stagger you want between your columns. So we've got our heads around the basic Ergogen structure here with the rows and the columns and the zones, and we've looked at the row overrides and the rows, to target individual keys within columns. So we're ready to actually start building this out properly. So to do that, we're actually going to install Ergogen on our own machine, and we're going to use this fork of Ergogen that I've used because that comes with the footprints that we're going to use here, and also comes with my config files for all the keyboards I've done. So if you want to just follow along and work with some of those existing config files, this is a great way of doing it, and you don't have to worry about installing the footprints separately either. So we can see what we've had there. We've run npm install, and we've now got Ergogen installed locally, and you can see I've included this input folder which includes the config files for all of my kind of keyboards that I've built here. So we've opened this piano config file, and then now the interesting thing is if you just copy this out, including the outlines section, which is a new thing that we didn't look at previously, we can actually see how this looks within the live preview. So the idea with the outlines is that you are defining a collection of different outlines based on certain properties in the config, and that's what then you can preview on the right here. All the little DXF files that it generates, you can switch the preview to display those. So we've got the demo one, which is those MX-sized keycap outlines, which are actually not much use for us when we're dealing with the chock size board. And I've finally created this preview.dxf, which is the real representation of the keycaps that I want to work with here, including these 1.5U keys for the pinky and the thumb. Now, as part of this outlines area, we're also going to set up the outline for the board itself. And you can see under here, if I get rid of this rectangle area, you can see that first outline is actually just trying to build itself based on the keys. We add this rectangle area to sort of represent this part of the board, and you can see they all overlap. So basically the area where these shapes overlap is what becomes the sort of fill for the shape of the outline. And you can see the outline here that's created by the rows and the columns. Now this comes from these bind values. So each key has a top, right, bottom, left bind value here that you set up. And so essentially that pushes outwards from each key to create overlapping spaces. So if you create a gap between columns by adding the rotate value, you can fill that gap in then by pushing out from the key. And you can see that's what generates the outline there. Now you can see here the way we've got these nice rounded corners. I've just switched to the preview of the cutout here. Now this one includes the fillet value, and that's what gives us the rounded corners. So you can see I've got the name attribute here, and that's what actually references the raw outline, and then so we're applying the fillet, which gives us the curves there. And then I'm creating these two new ones here, Keycap Outlines and Keycap Outlines 1.5, and you can see the difference being that we've got tags set up for these. These two will actually generate previews from two separate sets of keys, which we're using the tags item to create. So you can see the thumb key and the pinky key have got this tag value 15U set to true, whereas the default that we define at the top here under the key is the 1U set to true. So for the ones we want to change to 1.5, we actually just put 1U equals false and then 1.5U equals true. So for this one, we've got 1.5U true and 1U false, and that then puts it into that other outline essentially. So we've got two outlines, and you can see because we're using the 1.5U key, we want to rotate the key around because obviously the 1.5U keycaps actually go horizontally on the key switch, so we don't want a vertically aligned key switch for that, so we rotate it. Now you can see this final item under the outlines area is called preview, and that's just an array of other outlines. So you can see we've created a single preview here based on the output of two of those outlines. So this gives us our nice realistic keycap outline preview. Now you can see we've got this footprints area now within the key section. So this is how we actually say we want the chock switch footprints on the PCB in the position of each of the keys. So let's go ahead and build this, and we'll start to see what the actual output looks like. So you can see in the documentation here, there's this command for running Ergogen and actually creating the output for KiCad from Ergogen. So we're going to use this command here, and we're going to reference our piano config file, which is actually in the input folder. So we're going to pop that in there, and then we're going to do input, and then the piano config file name, and then -o, and then we're going to make an output folder and then a subfolder format. And this is kind of useful in a minute, and we'll see why. So basically the issue is with KiCad, you can't open the PCB files directly. You have to open it via a KiCad project. So we're going to just set up a little temp project within this output folder we just created alongside the actual keyboard output folder. So just inside this output folder, we create the temp project. And then all we do every time we run Ergogen to build a PCB file, we just drag and drop that PCB file, there it is there, into the temp folder. Then you can open that by double clicking it within the KiCad project. And you can see here it is. Now I've spent some time beforehand positioning everything, so it's all actually in the right place, but I'll show you how you do that. That's more a question of just fiddling with the XY positions to get everything in the right place. But you can see that we've got a key switch footprint in the right place for each of the keys. So what we're looking at here is the front of the board. So you're just seeing the sort of the red color is the copper layer for the front of the board, and the white lines are all joining everything up, and those are the connections. Again, we actually define those in the config file, which we'll jump back and take a look at in a second, but those are the connections that we need to make within KiCad, and which we'll come back and do later. But essentially this is all kind of electronically correct. Everything is connected in the right place here. Now let's just get rid of one of these hot swap footprints and see how that changes things. There were two footprints under the footprints area for the key. So we've actually still got the hot swap one, but now we've lost the ability to do the direct soldering of the key switches. So we've got rid of those through holes that were connected up now. So the only way this board would work is if you used the hot swap switches. So that would actually be all right for our use case, but I always kind of want to include the footprints for the soldering the switches in, just in case I did need to do that. So let's just pop that back. Now you can see this is actually the same footprint that we're using. It's just referenced two separate times, one for the hot swap and one for the non-hot swap. And you can see this has the hot swap param set to true, and that's why that works. It's the same footprint file inside Ergogen. But now we add them both, we can see these are the actual through holes that we can then solder the switches straight in if we needed to, alongside using the pads on the reverse if we want to use the hot swap sockets. So essentially you can just leave that as it is when you open this file and work with it yourself. We just need to know that we've got a footprint set up per key under that area. Now we can see that we've got some more properties that we haven't seen before, and that's the column net, and that's alongside the bind one, and these are all per key. So we added that rows item underneath each column to target individual keys, and then we can add the bind properties and the column net value. And the column net is just referencing one of the pinouts for the controller footprint. And the controller footprint is actually added under this PCB section. And you can just create a name for your PCB here, and you know that's what you put as the item, that's what creates the file name. And then you have an outlines area, and that's where we reference that final outline that we defined based on the sort of corner radius version of the raw output. We set that up as the outline for the PCB. And we can see that here. If we switch to that layer in KiCad, that is our nice rounded corner outline that we set up. And now we've added another item. Now this is this keycaps item in the outlines, and that's what's based on the combined keycap shapes that we created earlier. And I'm just going to put that into a layer in KiCad as a separate layer. So we're not using this layer for anything else, and we can just use it to represent our keycaps within KiCad. It's nice to be able to see the actual keycap size on the PCB as you're working with it. So I'm just tweaking the size of this rectangle here a little bit because looking in KiCad, we could see the keys were overflowing over that rectangle a little bit. So I've just made the rectangle slightly bigger. And when we open that now, we can see the keycaps there are just within the outline of that board. So that's okay for now. So let's jump back down, and we're looking at the footprints area inside the PCBs section now. So we've got this footprints system here, and then we're basically listing all the footprints that we want added to the board. So we've got the Pro Micro Pretty footprint, which is this amazing reversible footprint here that we're looking at now, and that's what actually allows the controller to face up on both halves of the board, because you solder the jumpers together to make this reversible. So as the board is reversed from left to right, you can actually keep the controller facing up by using that amazing footprint. So it's a really cool footprint that we're using there that's not included normally. Now we're looking at the vias here. So this is just a couple of vias to make it a bit easier to connect things up, because obviously the PCB needs to accommodate the reset switch and the slider switch being on both sides of the board. So adding some vias here, 2 for each, just makes it a little bit easier to hook that up. So you can see these footprints have all got this nets value, and if, depending on the footprint that you're using, you'll have different number of nets that you need to define values for. So you can see the PCM12 footprint here. This is actually the slider switch, and it's got a from and a to. So we're going to go from the raw item in the net to the positive item, and this all connects up within KiCad, and you'll see how that works as we get onto the routing stage. But basically you need to make sure that these things are all connected up to each other to make sure that it's kind of all sort of working technically. So this footprint represents the reset button, and you can see it's got 2 nets, an R1 and R2. They correspond to the pads in the footprint, and we're telling them that they're connected to the reset and the ground. So those are obviously pinouts from the main controller, and that's what basically sets up KiCad in a second to know that the reset pinout of the controller needs to connect to the R1 pad of this footprint. And you can see we've got the anchor property on these footprints as well. So we've got the rotate and the shift values. That's what positions it on the board. So you can rotate it around on the board and you can position it on the board. And so in the anchor area, we've got this reference concept where we've got the thumb fan, home, home. So we're referencing the thumb fan, thumb cluster zone, and then the home row and the home column of that zone. That's the point that we're then using these shift values to move the position of this footprint from. So you can see down here we've got the battery footprint, and that's just got the negative set to ground at the moment. And we need to tweak that a little bit in a minute, because actually those holes are slightly too big and too far apart. It worked fine on the last board I built, but I had to bend the pins out from the connector there a little bit. So we're going to try and fix that now. So you can see there's the nets value within the footprint. So we're looking inside a footprint file. Now normally you don't need to work too much in here. I'm just going to touch on this so that you can get an idea. If you look inside the Ergogen source folder footprints, then you've got these individual JS files that represent footprints. And those are basically based on the contents of a KiCad footprint file, which is within this area inside the backticks here, and then some extra config that sets this up to work with Ergogen. And you can see this is where the net stuff all actually works in real life. So you can see this is the variable, and we've got the pos net and the neg net, and that's what's represented up here. These are the properties that you can then specify when you're using the config. So what we want to do is make these through holes match this JST battery connector. So we're going to look at the actual product page to find out the dimensions. So the pins themselves are actually 0.7 millimeters in diameter. So we need to change the radius of the hole because they're slightly too big. So we're going to open up that bat.js file again, and you can see then that we're going to go up to the drill hole size here, change that to 0.7. And we've already adjusted this value to 0.75 so that there's a 1.5 millimeter gap between those two holes. If we then build that, open it in KiCad, we can see that our footprint has changed on the board. So we've got smaller holes and they're the right distance apart. And you can see there the positive, and we've set that up to match the ground pinout on the controller. It was defaulting to neg, but obviously in this case the pinout on the controller is called GND, so we've just changed that in the config to match that. Next thing we want to fix is this issue where the outline of the board doesn't quite meet the shape of the 1.5U keycap there. So we need to use the bind value to push out from that key into that shape. So we find that key, which is obviously the pinky key, and there's only one in that column, and you can see the bind values here. So we need to find the one that pushes it up and down basically to fill that space occupied by the bigger key. So we can open it up in PCB New and we can see now that we're getting there. We've pushed that line out a little bit now, so the yellow shape of the cutout board is now getting closer to the shape of the key, but it still needs to go a little bit further. So we're going to go ahead and do that. And we're going to bump those values up to 5 and see if that makes a difference. Okay, so now we can see the outline shape is about the right size, but it's created an issue. We've got a sort of gap between the corners here because the width that way isn't going far enough to sort of fill in the space there inside those little corners. So we need to push out from that key into the inside of the board to fill that space. So we're going to bump up that value. And we can see that's actually had exactly the right effect. So it's pushed into the space there, it's filled it up, and that's left a nice corner that then gets rounded off properly by the fillet part of the outline generation bit of the config there. So we're going to go ahead and export this to a Gerber file now. So we're going to make sure we've got an output folder specified here, and then we generate the drill files and click plot. And then we can jump back to the Finder and we'll see this Gerber folder. So we can go ahead and compress that just using the Finder compress tool, and that file is then ready to upload into PCBWay. And you can see almost instantly you get a nice little preview of both sides of the board here, and that's basically ready to order at this point. Now of course in reality we know it won't work because we haven't connected anything up yet, but it's nice just to get a little preview of how things are shaping up. So it's good to look at the outlines and the through holes and make sure everything roughly looks about right before you get too far stuck into the next process. And you can also jump into this kind of extended Gerber viewer within PCBWay as well, which lets you have a closer look, and you can turn on and off things here as you need to as well. So you can see I've started the routing process here, but I've actually got this the wrong way around. The pins on the footprint controller here aren't in a logical place. So the key on the left is actually going to one of the pinouts on the right side of the controller. Now obviously we want the controller this way around so that the USB port is on the right. So we can't actually just rotate it, but what we want to do is change the pins that match up. So we can see the switch on the left is using the P1 pin out from the controller. So we basically need to change that over to one that's on the left. So if we zoom in here, we can see the pinout labels for the ones on the left of the controller. So basically the P1, this is the pinky key, and this was connected to P1. We need to change that to P10, and then we'll go ahead and change these accordingly as well. So it's a question of sort of zooming out and looking where you want those routes to go. You're looking roughly where the routes have got to go past things to get to the pinouts on the controller. So you sort of imagine which one's going to make the most sense. Check which number it is, and then you can change the column net value in the config here to match that. So just going through and sort of working out where the routes are going to go here. I'll just speed this up a little bit. So I'm going to change those, build it, and then open it in KiCad. And we should see the white lines now look a little bit more logical. They're not crossing over the controller from one half of the board to the other. So now we can actually start the routing process properly, knowing that these are all in the right place. So it's a question of just clicking one of those through holes and then tracing a route to where it needs to go to. Now as soon as you click it, you can then only go to the thing that it's connected up to, so that because it's connected to the right thing using the net value, it knows where it needs to connect up to. So basically if you click one, you'll see the only thing it can do is go to the other lit up items on the board. So you can see this one needs to go to the pinout on the controller here, but also across to the other side of the switch, and that's how it will work when the board is flipped over. So you can see I'm connecting up to the vias that are in the center of this controller footprint. So the clever controller footprint obviously switches over according to which of the solder jumpers you solder on the board when you flip it over. So you're actually not connecting to the outside pinouts here, because that would force it to be the same orientation, which would actually mean it's flipped over on one half. Instead, it's going to the center things, and then from there the footprint will magically deal with getting those to the right pinouts at the edges of the controller. That means the trace routes have got to go through the little gap and then down into the middle. So you want to make sure you sort of allow yourself the paths to go through there from each of those. So you can see just dropping down between them from each of these keys here. Now this is where I made a little mistake and realized that I would cut myself off. So this trace route needs to be to the left of this leftmost P15 switch through hole here, so that I can then connect the P15s together. So I'm going to make sure this goes around outside to the left of that through hole there, and then down where it needs to connect to for the controller footprint. And now I can connect these two up here. So it's going straight to the footprint first, and then to the other side of the switch. And the same with that one. So what you can see here is the routes are trying to follow this 45-degree angle, but that's oriented vertically, and it does make it look quite weird when you've got your keys at these sort of varying angles. So what you can actually do is rotate the board in here, and then the trace routes will align with the key rows. So every time you're sort of routing a column, you have the board oriented in the right angle, and obviously then you can make it look a little bit neater than I am doing here. But because I find myself iterating through these boards so frequently, I'm sort of less and less concerned about making the routing look really nice at this stage, because I know that I'm going to replace it probably with a slightly tweaked version as time goes on. Once I realize I'm actually working on the final designs, I'll start paying a bit more attention to making this routing look a bit nicer. So you can see me swapping between the front and the back side here. So the green is the back side and the red is the front side of the board. And you can see that I can use that to connect things up without overlapping. So you can use both surfaces to give yourself some space to do this routing. You haven't got to make all the routing work on one side. I kind of was thinking I would use the green side, the back side, for all the ground connections, and then all the other connections can happen on the front here. So there are a few exceptions to that. And you can see what I'm doing here is connecting up the reset switch. So I'm coming from the vias to the reset switch, and then on the other side of the board I'm coming from those same vias to the reset switch on that side. And then as long as those vias are connected up to the right place through either side of the board, then it will all work. So you can see I'm trying to basically get this connected up here to that pinout on the controller, and in this case it was actually easier just to connect the pad itself directly to that. I don't need to go from the via. So essentially we're going through the pad to the via, and then out the other side of the board we can then find that. So I'm making some adjustments here because I kind of made a little mess of this and cut myself off basically. And you'll find yourself doing this sometimes. You create a route and then you realize you've cut yourself off. You can't make another route go through where you've just sort of blocked off with the route. So what I'm going to do now is make sure this route goes above all of the vias, and that means I can then use those vias to get back to the pinouts on the controller without this route causing me any problems. So these two vias we're using for the slider switch. And then on the other side of the board we can connect up that pad. On this side of the board, of course, we can route without worrying about what the red ones, the other side of the board, were doing. So we've got free space there. And we're just connecting this pad up to the other via. And because there's a bit more space on this side of the board, we can go ahead and actually connect this into the pinout on this side. So you can see this via needs to actually go all the way over and connect up to the positive battery terminal. So that's a little bit tricky now. As you can see, there's a lot of routes that are actually in the way. So I'm going to flip over to the back side and see if there's a path on this side, and it looks like there is. We can just go through this space here all the way over to the battery connector there, which is the positive, and then this is the negative battery connector, which needs to connect up to all the ground connections. So we can just start routing the ground connections now. We're on the back side of the board here. So these can basically all just connect up to each other, including these pads. So we've got one sort of central through hole for each of these switches, and then the pads, one on each side of the board, for the hot swap sockets. That pad is for the actual connection back to the controller. So I'm just connecting that to the through hole on the outside of the switch footprint here. And now we're back to a ground one here. This is a ground one, so I'm just connecting that pad actually directly to another pad, and then we're just jumping these all together. It doesn't really matter which order they go in as long as they're all connected together. So again, you could pay a lot more attention to how this looks. You know, it's a bit of a mess in this one, but my goal here was just to quickly create this board so that I can actually start using it. So I don't want to waste too much time rotating the board and making all this routing look neat. But obviously if it was more of a final board, then that's exactly the kind of thing that you do want to do. So you can see we're looking at the last of the white lines now, one of these ground connections. It just needs to connect up, and then we are complete with the routing. So I'm just actually looking at this, trying to think where it means it's not, you know, where there is a gap. So sometimes it sort of looks like everything is actually connected up to something, but in this case there is still a missing connection. So there we have, now everything is all connected up. So I'll switch to the silkscreen layer now. You can see a couple of these footprints actually had some content within the silkscreen layer. I'm not going to worry too much about that. Normally I try and get rid of all the silkscreen stuff to do with the footprints because I think it looks a bit messy. But what we do want to use the silkscreen layer for is a little bit of artwork. And we'll come back to that in a second. So we're just going to finish off working with these trace routes, and we're going to make them look a little bit nicer by using these two plugins. So we're going to round the tracks first. So every time we've got a corner, it's going to round that off a little bit. Now, weirdly, this sort of crashes at this point and it stops responding here. So it's all grayed out. So we're going to go back to the Finder. And we can see it actually has worked. It's made the new KiCad file here. So we just need to change the extension back to KiCad PCB properly, switch that over. Then we can open that from the KiCad project. That opens a new instance of PCB new. And here we go. So we can see the trace routes start to look a little bit nicer. They're sort of rounded off on all of the corners. The next thing we do is this teardrops plugin, and that will make the teardrop sort of shape where they join the through holes, which just looks so much nicer. So this is definitely not the neatest routing that I've done, but it didn't take very long. So it was a question of doing it quite quickly. So you can see there's this weird little X that's showing up over this route. It's actually talking about the backside on the green layer, the green copper layer. So we'll switch to that and we can see what's gone wrong. So it's actually just because the trace routes are meeting in the middle of each other basically. So we can see this kind of fork shape here, and that's what's caused the problem basically. It's sort of disconnected actually at this point, and there's an issue sort of here where this join happens. So basically I need to reroute that to not have that fork, and I didn't realize this when I was recording the video. So I'll make sure the version that I have available to download has got that issue fixed. But it's interesting to notice that would result in that issue if you use this plugin with routing like that. So let's go ahead and get some artwork onto this board. So I'm going to jump into Sketch here, which is a really cool vector artwork application on the Mac. And I'm just going to basically design a little bit of artwork for this keyboard, which I'm calling the piano. So what we want to do here is export the text into the silkscreen layer, but I want the icon itself to be part of the copper layer, and to shine through, that means it also needs to be in the solder mask layer. So there's a cutout in the solder mask to let the metallic copper layer shine through. So we're going to turn this layer off for this first part. That's ready there, and then we're going to open this bitmap to component app from KiCad. Now you can't open that directly, that gives you an error here, but what you can do is open it from within the KiCad project. They're the same as with the PCB new files as well. So that's not that icon, it's that one. And you still get another error here, I'm not quite sure what's going on there, but it does open, you can see it in the dock. And then go to it here. So now we just basically need to drag in that JPEG from Sketch, and we can click Load Bitmap, and then we can just use the export for this slice and drag it into place. So we need to make sure it's a JPEG first, because it works from a bitmap sort of image pixels, and we're going to drop it into this location so that this application can run it. Now you can see the size there was a little bit small, so the actual sort of detail in the pixels here isn't very high. We're going to go through the process and see what that looks like. The other thing that's important is the DPI value here. So basically the values you enter there dictate how big it's going to be on the PCB itself. So we hit the O key on the keyboard and then click, and then we can find our exported footprint file here. And you can see the shape is a bit weird. The text has gone a bit funny. Let's switch to the silkscreen layer so we can see it in a bit more detail. So you can see the shape of the letters has kind of gone, and that's just because there wasn't enough detail in our original JPEG that came out of Sketch. So we're going to go back and we're going to drag in a higher resolution output from Sketch. We're just going to change that to 2 times size here for the export, and then we can drag it in. And we'll see the preview looks bigger, and we can see there's a lot more detail there. So I'm exporting this, and I've left the DPI at 72, so we're going to see what happens if we do that. So just going to delete that one, click again to place it, and find it there. So this is high resolution, but the DPI was set to 72. So that means it's actually massive on the board, which is no good to us. So we're going to increase the DPI value again. Click to place again, and we can drop this on. So that's looking about the right kind of size now. So we're going to click where we're happy with that going. And by default, that's gone into the silkscreen layer, which we're previewing now. So that's all good. So now what we want to do is switch to the icon itself. So we can go back to Sketch, turn off the text layer and enable the icon, and then drag this out. So we keep the size exactly the same. So it's 2 times size in Sketch, and we're going to make sure we use the same value in the DPI here. We're going to call that one piano icon. And then when we click to place this, we can drop this in and it'll be a separate item. So we've got to search for it again because obviously it's not under recently used, it's a new one. And we can click and place it, and we can see the scale all matches up. So it's going to go into the silkscreen layer by default. So we want to move that into the copper layer and also into the solder mask layer. So we're going to right click on it and click Open in Footprint Editor. And then we can actually select the vector components of this artwork. And then we can click Properties for each one of those. And that will actually allow us to change it to a different layer. So you can see it's in the silkscreen layer. We want to move that to the copper layer. We're just going to put this artwork on the front. So we're only interested in the front one. And we do that for all 3 of these vector shapes here. And we click that little button to put it back onto the PCB, and we can see it's gone into the copper layer. Now, by default, that's not going to be visible yet because it'll be underneath the solder mask because we haven't done anything to make that shape shine through. So let's go ahead and use the 3D viewer to see what that might look like. So you can see the copper layer is there, but it's covered up by the solder mask. So you'll see a kind of 3D shape of it almost on the surface of the board, but you won't see that metallic shining through. And this can be quite an interesting effect, perhaps if you actually combine it with a cutout layer in the solder mask as well, you can kind of create an interesting effect. Depends on what kind of color solder mask you have as well as to how effective that's going to be. If you look at the flame keyboard that I did, that has artwork that's based on a different shape for the solder mask as the copper layer. So you get some fully exposed and some partially covered up copper layer by the solder mask. So you can see the 3D viewer is trying to kind of show us what that might look like. In real life, it's actually probably even more obscure than that. So basically we need to get that shape into the solder mask as well. So we open the footprint editor again. And we're going to just duplicate these shapes now. And it attaches to the mouse after you do that, so you sort of got to click it back on exactly the right space again. And then we can click Properties and move it into the solder mask layer, which is f.mask for the front. Do that with the other 2 shapes. Click that icon to save it back to the PCB. And now if we look at the mask layer specifically, we can see that it's in there as well. So that means it's going to cut out that shape from the solder mask in addition to putting that copper layer down as well. So we now get this nice effect of the text in the silkscreen and then the metallic. If we use the gold finish for the surface of the copper layer here, we'll have a really nice effect here. So let's export this. So make sure we haven't got any Gerber folders or files, and then we're going to go File and Plot. Make sure we've got that Gerber folder name at the top there. We can generate the drill files, and then we can click Plot and close. And then that Gerber folder just needs to be compressed to turn it into a zip. And then back to PCBWay, we can click Add Gerber File and upload it. And we'll see our final board with the artwork and everything ready to go. So again, you can use the fancy viewer here to get a bigger, sort of more interactive preview of this Gerber file, just to make sure everything looks about right. And you can flip it over. So you can see the reset footprint and the slider switch footprints on both sides of the board there, along with all the other footprint parts. So now it's just a question of making sure the settings are all okay on this order page. So basically that's just a question of choosing what colors you want for the solder mask and the silk screen. So I'm going to go for matte black because I like the matte finish much better than the glossy ones. That means it's obviously sensible to have the white silk screen. And the other thing that's useful to change is the surface finish. So it's sensible to go for the lead-free option for the surface finish, and if you want to pay a little bit more, you can get the immersion gold finish, which gives this nice gold look to it as well. And then it's really just a question of choosing your shipping and clicking Save to Cart. Now at this point, they'll actually go ahead and jump in and look at your Gerber file and make sure there are no obvious issues with it. And obviously, it's not going to guarantee that it's going to work for the keyboard if you've got some routing misconnected or anything, but it'll make sure that they can actually manufacture it. So they'll approve it. And once it's approved, you can go ahead and check out, and you'll get that great PCBWay service, and it'll arrive and you can take it to the next stage, which is soldering it all together. And that's going to be another video, so do make sure you're subscribed with the bell notification, all the rest of it, to make sure you get that video. Now, if you've enjoyed this detailed video, obviously it took a lot of time to put this together. Many thanks to PCBWay for sponsoring it, because it's actually them that allows me to keep videos like this free and not behind any kind of paywall. So it really is thanks to them that this content is free and available to everyone. So I'm super pleased that I'm able to do that. So don't forget to like, share, comment and subscribe, and I'll see you in the next video.